So, good morning, everybody. It's a great pleasure and honor for me to be able to speak to you today here at this very nice and very fruitful workshop. The topics I'm going to speak about, they are not quite related to heteronuclear species, and also they are not related to dipolar gases, obviously then. But still, I hope you will find lots of things to connect with all the other talks that have been there. I'm here from the University of Heidelberg. So this is Heidelberg. We're just now moving to a new building which has been built somewhere here. So beside the labs, everything is ready. So we'll be hopefully able to move in pretty soon. So what I'm going to talk about is deterministic few-fermion quantum systems. And as you will realize, there will be many connections to all the other things that have been discussed, like one-dimensional physics, polar physics, and so on. You will see. First of all, let me just briefly tell you what we're working on in my laboratory, in my group. The first topic that we've been working on for quite a while is really universal three-body bounds at Efimov triatomers, which have been an active topic of this workshop. There's not really new stuff that we've been doing on this, so I will not be talking on this, because we are setting up a new experiment that will deal with actually three-component Fermi gases in an optical lattice. It's actually quite far advanced now. We're just starting now to set up the lattice to load atoms into that. But what I'm really going to be talking about today is our finite Fermi systems with controlled interactions that we can prepare in our laboratory. And you can really, for the rest of the talk, think of these systems as being trapped in kind of a one-dimensional trap, more or less harmonic trap, with now spin up and spin down atoms that we can fill in at wish, and we can also control the interactions. So first of all, the motivation. Why is it at all interesting? What we can really realize in these systems is isolated quantum systems where we can really control all the degrees of freedom. So any excitation of the system can really be controlled, with quite good fidelity. And then, of course, it's very interesting in such finite systems to study pairing and all the different interaction regimes, be it very weakly interacting, so you form simple pairs of two atoms, or you make it much more strongly interacting, then you form systems that are kind of similar to polarons. And of course, on a longer term, it will also be interesting to study the dynamics, which we haven't done so far in any way. So now here's the outline of my talk. First, I'm going to present you how we are actually preparing these few-fermion systems in the laboratory, so you can get kind of an idea what we can do. And in the second part, I will show you the first experiments with repulsive few-body systems, where we can show kind of fermionization of these systems when the interaction becomes strong, and when we even make the repulsion even stronger, the system obtains kind of magnetic correlations. We get spin polarized systems out of mixed systems in this way. And the third part of my talk will be devoted to attractive few-body systems, where then we study correlated tunneling, so pair tunneling out of such systems, and we also observe the pairing to be quite dependent, of course, on whether you have an even or an odd number of particles in the trap. So first of all, how do we repair these guys? We start with a quite conventional ultracold Fermi gas, which is actually not that degenerate, which helps us so that we can really do fast evaporative cooling at even moderate interaction strengths. We start with a Fermi gas which is about at half the Fermi temperature, about 250 nanokelvins, in such kind of a trap, 100 microns in size. To this, we superimpose a quite tiny, few microns sized trap with a trap depth which is on the order of 3 microkelvins. So that trap depth is much deeper than the Fermi energy of this macroscopic cloud here. And so it doesn't really affect very much the properties of our reservoir, if you want. And so in this way, if we assume somehow that there's thermal equilibrium, we can simply assume now the Fermi energy of the whole system is now simply more or less the trapped depth of this whole system, which is then the order of 3 microkelvins. And from this you can calculate a new T over Tf, which will then be on the order of 0.08. Yeah? If, of course, which we cannot test very nicely, the system is in thermal equilibrium. So what this means for the occupation probability of the lowest energy states in the system, is you just take Fermi-Dirac statistics and you come up with a number which is very, very close to 1. Yeah? And then there's nothing else to do than really removing the reservoir, and you should have this very highly degenerate sample. And that's what we take as a starting point for our experiments. In this tiny trap, we have a few hundred atoms. And we simply now apply a magnetic field gradient, which gives us which superimposes to this kind of a potential, a linear gradient. And in this way, we can somehow control pretty precisely the exact number of bound quantum states in this tiny trap, yeah? Which then leaves us with a particular number of atoms that's just the same as the number of quantum states in the trap. So this is kind of the classical analog, which has been kind of on there's kind of this tradition that students who graduate, they get this very nice hat with all kind of funny things on top that kind of relate to their thesis work, and that was Friedhelm Savane's PhD hat, how we call it, yeah. And so here is the reservoir of atoms, and from this reservoir we can fill kind of a tiny trap, and it's gonna be tilted and spill, and so we can spill almost all the atoms, besides only very few, in this case 4 atoms. It works actually pretty well, yeah. It is almost deterministic source of atom numbers, yeah. But of course very classical. So how does this work in a real experiment? I just give you kind of in a short way the final result. This is, for example, if you tilt the trap so much that there's only one quantum state present in the end. And what's shown here on the left-hand side is a histogram of many implementations of the same experiment, recording simply the fluorescence signal after recapturing the atoms into a magneto-optical trap. And what you can see from this graph here, first of all, we can very clearly distinguish individual atom numbers, so we can tell with a very high fidelity how many atoms exactly we had in the trap in such an experiment. And what you can also see, in this way, we can very nicely prepare, for example, here with about 96%, fidelity, we can actually prepare 2 atoms, and we can also prove that these 2 atoms are in almost all the cases in the ground state of the trap. The same thing also works for different numbers of atoms. For example, here is shown the situation of 8 atoms. So 4 spin up, 4 spin down. And I'm not showing this here, but what we can also do, we can separately control the number of spin up and spin down atoms in the experiment by simply choosing a magnetic field where the magnetic moment of the 2 states is very different. The next thing that you need to know somehow about this system before we start some physics is that the aspect ratio of the trap we are using is about 1 to 10, which means that if the atom number is as small as this here, these are only 4 vibrational levels, the system will be in a one-dimensional regime. Yeah, so you can consider really for all of the experiments that are going to follow, you can consider the system to be one-dimensional. And so what this means is that now you have to really rescale your scattering length to obtain a one-dimensional coupling strength, and for the parameters we are using, it works really well to assume the coupling strength that you obtain from simply assuming a one-dimensional tube and using the formula that Massimo Olciani derived in this paper here. So that basically gives you the following thing. That will be the scattering length as function of magnetic field here. For the system we are using is actually the 2 lowest hyperfine states of lithium-6. And what you obtain is this kind of situation, so basically a resonance that's shifted to a range of positive scattering lengths for the 3D case. Okay, so now this brings me to the second part. Now the first thing we'd like to study is the repulsive few-body system. Yeah, and there's two words that I'm mentioning here: fermionization and magnetism. And so first of all, some of you might be puzzled. I've just mentioned to you that the system is one-dimensional. There should be no magnetism in one dimension. Yeah. So in one dimension, and that has been shown a long time ago, the ground state of such a state should be unmagnetized. That is, for example, proven in this paper here by Lieb and Mattis, where they basically consider like a number of electrons in a one dimension, and they basically prove that, you know, any system that has some particular magnetization will always have higher energy than a system where that is spin balanced. For example, this system should have always a lower energy than this one for any interaction strength. And so there's nothing wrong with this paper. The mathematical proof is actually completely right. Yeah, and so we'll see in the course of the talk why still there can be some magnetic correlations in the system. So before I talk about the magnetism, I should explain you how we actually do experiments with this system. First of all the experiments that I'm going to show you today is really by observing tunneling dynamics of this tiny trap, out of this tiny trap. For example, here in this case, what I'm showing you is two particles in the trap, and what we do is we tilt the trap so much that the highest lying states in the trap have a tunneling time scale out of the trap that will be experimentally accessible, which means it should be on the order of 10 milliseconds to 1 second. Yeah? So and then we basically observe tunneling out of this trap, and from this we can infer, for example, the total energy of the system. So there's just a few sample curves of what happens for different interaction strength, and what you for now should only see is this kind of the mean atom number plotted here versus kind of the whole time in this tilted trap. And so what you can see is that all of these curves, they somehow end more or less exactly at one atom. Yeah, so which means that for the experiments I'm going to show you now, we can somehow consider all the tunneling dynamics to happen only to one atom, so one atom tunneling, one particle tunneling, which simplifies quite a bit the analysis. Yeah? And so basically we can now determine kind of a tunneling time from fitting exponentials to these curves. Yeah? Okay, so that's what we do here. And first of all, to give you some insight, I will show you experiments where we use only two atoms. Yeah? And we have this very nice advantage. We can use one spin up and one spin down atom which will be interacting in an S-wave interaction, and we can compare this system also with a system that is spin polarized. So putting in two spin polarized atoms which will be in this configuration, and where there will be zero interaction strength, and so the system should not depend on the magnetic field we apply. So this will kind of give us kind of an experimental way to actually calibrate our trap. So and what's plotted here now is as we increase the interaction strength, so we basically repair the system at zero interaction somewhere on this side here, and then we crank up the magnetic field, applying more and more strong repulsion between the two atoms, and we observe the tunneling timescale out of such curves here as a function of magnetic field or interaction strength. And so what we can observe here, so this is this blue data here, and the green data here, these are actually the numbers obtained for this particular implementation, where the tunneling time should not change as a function of interaction strength. Yeah? And what we can see here in this graph is that, of course, as we crank up the repulsion between the two atoms, the tunneling time gets shorter and shorter. So one atom is expelled out of the trap faster and faster as you increase the repulsion. Yeah? And then there's one particular point in magnetic field or interaction strength where the tunneling time is exactly the same as that of the two identical fermionic atoms. And that's the point which you call where the system should be fermionized, because the relative wave function of the two particles should have the same modulus square at this point. Yeah, so that's how the system should be fermionized. And now, if you would like to think of this as kind of a one-dimensional gas, it's only two atoms. Yeah, then this regime up here, above this line, this should be the Tonks regime. So strongly repulsive one-dimensional system. And on this side, because this is no longer the ground state, I will show you in a second, this is the so-called super Tonks regime, which was for the first time studied here in this publication. Okay, so now this is kind of two atoms. It's kind of simple. We can actually solve this. Can be solved exactly. It has been done in this paper, for example. And what happens exactly? Yeah. So here, what I plot here now is minus 1 over the one-dimensional coupling strength. So basically 1 over this parameter. So that 0 will be here in the center. And I'm actually I'm starting on this side here. Yeah. Okay. So so here's positive repulsive interaction between the two atoms. So that's where we start. And now what we do is we increase the repulsion in the system as we go up here. And that means simply we are shifting all the vibrational levels in our trap up, for example, here by 1 times the axial trap frequency in the trap. Yeah, and this point should then be the case where the two interacting particles behave exactly as two spin polarized particles, so they acquire a wave function which looks like this. Yeah, and as we go even further, yeah, now the energy is increased even more. Yeah, so the energy is increased beyond the point, beyond the energy that two spin polarized particles would have. Yeah, and that's now the situation which is the so-called super-Tonks regime, and which has not been covered, for example, in this publication. Yeah, and that's why in this publication, of course, they did not observe the case where this particular system, for example, can have a higher energy than this one. Yeah, but as we go across this resonance here, where G1D diverges, we can actually have an energy that's larger than that of the spin polarized system. So now that's only for two particles. Let's see. Just here again, it's kind of the tunneling dynamics. So this would be for weak repulsion. This curve here would be for the resonant interaction strength, and you can see these green points here again. It would mean this is the spin polarized system, just for comparison. And you see also the dynamics of a spin polarized system will look exactly the same as the dynamics of two distinguishable particles right on resonance. Yeah? So there's still two particles, and as you go further to the and make the system even more repulsive, then the one particle tunnels out very rapidly from the trap as the energy is increased even more. So now we can apply this to three particles, and we can ask what happens. So we start with two spin up and one spin down particle. Now we can have this situation that one spin up particle leaves as we tilt the trap so much that one particle can leave, or we can obtain a spin polarized system and the spin down particle leaves. So we can study this as a function of interaction strength. That's what plotted here. And you can see as we go for very weak repulsion on this, that's on this side here, the probability that the minority particle tunnels, so that would be this situation that you obtain afterwards a spin polarized sample, should be 0. Yeah, that's what's very much expected. Yeah, I mean we all know that. Yeah. So now as we increase the repulsion, we go on resonance. What we should expect, because now the wave function should be fermionized, we should expect that there should be no real difference between the three particles, and so every three of the three particles should tunnel with the same probability. We should get 1/3. Yeah, if you look at the numbers here, it looks quite reasonable. Yeah, and then as we go even further, the probability for this blue particle to leave here will be larger than 50%. Yeah, so with the probability larger than 50%, we'll get this kind of situation. Yeah. Okay, we can drive this to even more particles. We can put in, instead of 3, we can put in 4 or 5 particles. So there's these other additional curves here, and that's the kind of the most extreme case we've studied so far. So 4 spin up, 1 spin down particle, and we can do the same experiment. We still get up to 50% probability that the minority spin down particle leaves the trap, and we obtain a spin polarized sample. So now this is kind of an extreme case, because we start with this kind of situation where obviously the spin down particle sits in the lowest vibrational level of the trap, but if we make the repulsion strong enough, yeah, we can make this single spin down particle leave the trap first with 50% probability if we tilt the trap. Yeah. Okay. I find this kind of intriguing, but it's, on the other hand, it's also what you can expect. Yeah, that if you increase repulsion beyond this point of resonance, that exactly this should happen. Now, the last thing that I'm going to show you here is now the situation of 4 particles, 2 spin down and 2 spin up particles. Yeah, we do the same thing, but now, of course, it's no longer here the probability of having minority particle tunneling, but now what we study is the probability of creating a spin polarized sample. So what we do now is, as we increase the interaction strength, we allow 2 particles to tunnel. Yeah, and what we do is we count the probability of observing a spin polarized sample, meaning obtaining either 2 spin up particles or 2 spin down particles. Yeah, so this is what we try to do, and that's what the blue points here depict. Yeah, so the red points here, that's the case, probability of creating a spin polarized sample for this extremely imbalanced system, 1 spin down and several spin ups. So this is now the spin balanced case, and what we observe actually a quite similar curve, and as compared to the imbalanced case, and here the probability goes up to 60% to really create a spin polarized system. Yeah, and this is kind of for us a very clear indication that the system obtains kind of ferromagnetic correlations. Yeah, as there's 2 particles of the same spin type have to tunnel first. I mean, they have to be higher in energy. Yeah, and thus they also have to be. If you look at the expectation value in space, they should also sit further outside in the trap. And somehow, in this way, this means you have somehow a crossover going from antiferromagnetic correlations, where you always have kind of a spin balance system, going to a ferromagnetic situation where you have, with quite large probability, a spin separated situation. Okay, so what can we learn from this? Is this really a tiny ferromagnet? Actually, I'm not quite sure of the answer myself, yeah? But what I can tell you, first of all, what's kind of important to take to consider here is the system that we prepare. It's not really the ground state of the system. That's the first thing. So it's not contradicting any mathematical proofs. There should be no magnetism in 1D or something like this. Yeah. That's the first thing. But this is actually something that holds for all of the cold atoms experiments that we do, also in 3D with repulsive interactions. Yeah. So there will always be the molecular bound state underneath. Yeah. So that's the same thing. Yeah. The second point here is, of course, this magnetic state occurs only on the negative side of the confinement-induced resonance, so for negative values of G1D. And then the third point is that it needs to be considered the system is finite, yeah? So there's no phase transition, yeah, because it's a finite system. And furthermore, and that's very nice, and that's also something that's, of course, related to the finiteness of the system. Our system in this magnetic situation is perfectly stable as far as we can see. We tried to hold this system for times as long as 0.6 seconds. After that, we didn't quite dare to hold it much longer because we had some difficulties of heating up some coils too much, and then the system becomes a little less stable and not so reproducible anymore. So we don't hold them very long, but 0.6 seconds, after 0.6 seconds, we didn't observe any decay of the system. So we couldn't really measure any decay of this system at with repulsive interaction strength. Yeah, and this of course has to be compared with the 1.5 kilohertz trap frequency. So that means the system is really stable for our experimental conditions. Okay, so I mean I would of course be glad to hear some comments from you on what kind of implications this has. Okay, now for the last part of the talk. This is now the attractive system that we study. Now we are not going for starting from zero interaction, going to positive coupling strength, but we are now going for negative coupling strength, making the particles attract each other. Now this is actually a situation that's a little bit more difficult to analyze for one single reason. Yeah. For attractive interactions, if you have 2 particles, for example, in the trap, so the 2 particles are always like the easiest ones. Yeah. So the energy is reduced as we increase the interaction strength. And what it means is that now, if you have 2 particles, for example, in the trap, so the 2 particles are always like the easiest ones, yeah? So the energy is reduced as we increase the interaction strength. And what it means is that now, if you have 2 particles, for example, in the trap, so the 2 particles are always like the easiest ones, yeah? So the energy is reduced as we increase the interaction strength. And what it means is that now, of course, the tunneling time, so that would be very weak interactions, the first curve here. These curves, they get slower, yeah, as we increase the attraction strength. But there's one other thing, yeah. In all the previous experiment, you've seen we could treat the tunneling of the trap usually as a one-particle tunneling problem, yeah. And now here, what you can see is we'll always lose, for example, in this two-particle experiment, we'll always lose two particles in more or less the same period of time, yeah. So we have to really consider correlated tunneling out of a system, which is more complex, but of course also more interesting. Okay, so this is what I said already. But now what we can really learn from this, and we have some quite preliminary analysis of the situation. So what can actually happen, yeah, in this way, yeah, starting from two particles after some particular time that we wait, and then we and observe the system. The system can, either one particle can have left the trap, or two particles can have left the trap, and that could have happened in different ways. For example, the two particles can have just left one after the other one, or the two particles have gone together, yeah, as a pair. And so what we do to kind of analyze the situation, we basically take the expectation value of the number of particles we observe for a particular point in time, and that's plotted here on the horizontal axis, and we plot this against the probability of observing this kind of situation, yeah, that there's one particle left in the trap. And this should give us some idea to distinguish also between these two processes. And especially, first of all, whether there's some correlation between the two particles leaving the trap. And now, of course, it's very simple to just calculate what the probability would be for the two particles just leaving one after each other totally uncorrelated. So that's this black curve here. And for very weak interaction, for very weak attraction, we more or less observe exactly uncorrelated tunneling. And as we do have to, how much time do I have? Okay, that's fine. Yeah. So, but then as we increase the attraction, you can see that the probability of observing one particle is being reduced more and more, and until it becomes more or less negligible at strong interaction strengths, which tells us that more or less in all cases the two particles tunnel together. Okay, so that's kind of very preliminary, and we are still trying to get some ideas of what exactly is going on and what we can really learn from this. But before I conclude, let me just mention some other experiments that we've done, and that's basically studying how the energy of the system evolves as we increase the system size. Yeah? And what we plot for this purpose here is the ratio of the tunneling time out of a trap over the tunneling time of a non-interacting system. So that would be the tunneling time of an attractive system compared with the tunneling time of a non-interacting system. And we start, of course, like one particle is boring, yeah. So there would be no difference between interacting and non-interacting, yeah. So that will be 0 dBs here. And then we put in two particles, and we basically take the ratio of these two particles interacting, not interacting. So that's kind of a 6 dB increase in this ratio. And now, as we add a third particle, so that's this point here. Well, this third particle, it can only kind of weakly bind to this pair in this lower vibrational level. So it will not be so strongly modified. And then as we add a fourth particle, of course, this can now pair up with the other spin down particle. So there will be strong attraction to that. And of course, it will also be attracted to these guys down here, and so on. So you can see kind of this typical odd-even effect that you also know, that's also known from nuclear physics. Okay, and we've done this up to kind of for this kind of systems. Okay, yeah. And with this, I would like to conclude. First of all, we can prepare very nicely few-fermion systems with kind of control that has been kind of unprecedented, really. And we can have control over both attractive and repulsive interactions. For repulsive interactions, we observe we can create these fermionized states, And we can also observe magnetic correlations in this repulsive few-body system as we go across the confinement-induced resonance. And for the attractive system, we can observe correlated tunneling and kind of an odd-even effect in this situation. Okay, with this, I would like to thank you for your attention. And of course, I would also like to thank my team that has been working extremely hard and very carefully to obtain all these results. And the major people on working on this few-fermion stuff were here Friedhelm Servane, who just graduated last fall, whose PhD hat you've seen during this talk, and Gerhard Zürn is responsible for most of the more recent work being done on the experiment. And with this, thank you very much.
Thanks, Selim, for that wonderful talk. Literally instead of this guy, but let's just pretend that it's still working. There's questions. Does it work? Let's pretend. It still has something. Anyway, something. Is it working? Oh. Anyway, I'm not quite understood why you call anti-ferromagnetic the state which to me is just unpolarized state.
Okay, yeah.
Paramagnet.
It's just, yeah, you can call it paramagnet, that's fine. Okay, yeah. Okay, this kind of this itinerant situation where you don't have pin the particles in a lattice, yeah? Yeah, and then of course, you know, if it's completely mixed, yeah, so you always have, you know, no matter what you do, we'll have complete equal mixture of spin up and spin down. This is what I call antiferromagnetic here, yeah?
But they should order, you should have a staggered order.
Okay, yeah, that's not there, yeah.
Call it antiferromagnetic.
Okay, I agree, yeah, that's right.
So in this diagram where you showed the leaving time after, as a function of interaction, where you showed that fermionization, can you follow the other branch as well? So because there should be an attractive branch.
This thing?
No, before. Yeah, this one.
Yeah, so that would be the one branch in this picture, right? This would be this branch.
Yes. Can you follow the other one?
What we can do is we can go like this between these branches. Yeah, using RF spectroscopy. Yeah, we can flip the spin of one guy, and we can really go. It's very nice. Yeah, we can go. It also works for more than two particles. Yeah, we can go like from a state here to a state here, or from a state here go over there. Yeah, so that.
So you can map also the other one.
You can. Yeah, we can map the other ones as well. Yeah. Okay. Yeah, we tried that.
And regarding the multi-particles, so how would you expect it to evolve when you put more particles, the ferromagnetic transition? So you expect to see a sharp transition, or it will blur into decay?
So first of all, yeah, the system is stable. Yeah. So the system is stable. You know what you see here is, you know, there's some range where there's a dashed line here. Yeah. In this range, the system is sometimes stable, sometimes not. Yeah, there will be resonances. Yeah, where the system couples to molecular states. Yeah. So we have to run fast over this and go up here where the system is stable again. Yeah. So the more particles you add, the harder it's going to get. Yeah. So I'm not sure whether you can, directly conclude that this is going to work for a thermodynamic system, kind of. Yeah. That was your question. Yeah. Whether how stable it's going to be. Yeah. It's probably not going to be terribly stable. Yeah. In any case. Yeah. Maybe, but probably more stable than the 3D case. Yeah.
So in this plot, one thing I don't understand, you said that with 4 particles you expect that at 1 over g equals 0, the probability is roughly 1/4? For the 4 particles.
That would be for this case, for the, okay. That's for this, these particles.
Yes.
4 particles, 1 minority. Then it should be 1/5. No, 1/4 is right, yeah, sorry.
1/4.
Yeah, 1/4, yeah.
And in the data it looks like...
It's a little bit lower, yeah? It's quite a bit lower, actually, yeah? So this one here.
So, yeah.
But it's also not yet on resonance. So what turns out is the more particles we add, the harder it gets to go on the resonance, yeah? So you see there's no point on resonance here. There's only one point across the resonance for the 3 particles, yeah? Because there, in this range, it's going to be unstable, yeah? So you will see some, it's actually funny, you can see some oscillations also between molecules and free atoms, yeah? So it couples to molecular states, yeah? And so that's, so yeah, this point might also not be so good anymore, yeah? Because it's too close to where it becomes unstable, yeah? Yeah, it should be it's right, it should be 1/4 here, yeah? It should be up here, yeah? But you see this is also going up very steep here. Yeah, so I don't know what exactly would happen to the black curve, yeah? Yeah. But it's a good point, yeah?
Yeah, it's very nice to see these fantastic things. Actually, I'm just a bit confused by this picture, and probably you can help me in understanding what I'm doing as a mistake. I mean, what concerns the lower states of this trap, this is a harmonic potential.
Yes. It's not quite harmonic anymore as we tilt it, yeah? So there's some difficulty with this,
exactly.
Yeah?
And as soon as you tilt,
yes,
and you get an harmonicity,
yes,
am I right when I say that you are going to have more confinement-induced resonances? So the higher you go, the more resonances you will have between, let's say, the scattering channel
there will more. Yeah, exactly.
And since it is anharmonic, this is allowed.
The anharmonicity, what the anharmonicity helps you with is especially the coupling to all these molecular states.
If it was perfectly harmonic, you would have only one.
Yeah, then the coupling would also be much weaker.
Mm-hmm.
Yeah, because you would have, I think that maybe they will become degenerate, but it should be always the same number of crossings.
Yeah.
But the coupling will be weaker. Yeah, they could be degenerate. Yeah, if they
would be forbidden.
But the same number should be always there. Yeah. But then if you are perfectly harmonic, then they would be more or less forbidden. That actually helps. Yeah. We haven't really investigated that, but I think one can tune the stability in this way. I mean, that's probably what you're also referring to. One can probably tune the stability of the system in this dashed region, yeah, if you make it more harmonic.
Yeah.
It hasn't been done yet, yeah. We haven't tried this. It should help quite a bit to make it even better, yeah. Because so far we haven't tuned this. I mean, you can simply just squeeze the trap quite a bit so that you can ramp fast for adiabatic for this particular system, but you will have very weak coupling to molecular states. I think it should work, yeah? So there's one other remark for this. I think this point here is also off. This should be 1/3, yeah? This point for the spin balanced case, yeah? But it's also slightly below the resonance, yeah? So, and it's also the most unreliable point, I would say, yeah? Very close to the resonance, yeah?
Probably somewhat related to the previous question, but let's say you want to keep the trap as harmonic as possible.
Yes.
Now, the tunneling, of course, it's exponential in the height of the barrier, but also in the thickness of the barrier. So, is it possible to do an experiment so that it's as harmonic as possible with very thin wall, very thin exit?
We will get better in that respect because we'll make a smaller trap. That will help. But I think if you really want to do an experiment on a harmonic or a harmonically confined system, then probably the tunneling experiments are not the best experiments to do. Yeah. But what we have also some other set of experiments already that we have done, which I haven't shown. That's doing RF spectroscopy in the system. Yeah. So we can flip the spins of individual of these guys, yeah? And in this way, we can also probe kind of an energy landscape of individual states, yeah? So we can have kind of, it's like atomic spectroscopy in principle, yeah? So you excite individual electrons in your system, yeah? So this somehow we can also do, yeah? It works especially well. So what really works so far, what works well is kind of these kind of systems, yeah? Kind of where you have only one minority particle and you flip the spin of the minority particle. That's kind of simple to do, yeah? Because you kind of have the same system with just different interaction afterwards, yeah? And that works really well, and there you can really go for more or less perfectly harmonic system because you just squeeze the trap a little bit to remain in the harmonic region, and then you can really do this is actually what you want to do if you want to do experiments in a nice harmonic trap. They will be much more quantitative, yeah, if you want. Yeah.
Okay, urgent. One urgent question.
I'm just a bit confused here. Where is the molecular site on the positive side?
Because I've plotted this minus 1 over G1D, right? So that's kind of, sorry about that, yeah? So why do I plot like this, yeah? It's because we have the magnetic field going like this, yeah? You see, if we have, whoops, where did I plot it here, yeah? So the magnetic field goes this way, and I wanted to plot for somehow, there's only this graph left, yeah? So I could have plotted it the other way, yeah? But somehow we start from the left and go to the right in magnetic field, yeah, and that's why I wanted to keep the direction the same, yeah. This makes it kind of annoying, yeah. Sorry about that. So in all the plots, so here the molecule will be on this side, yeah, and now this is kind of what I plot here is really the one-dimensional tube. So the bound state goes to minus infinity right on the resonance, yeah. In a real 3D case, this bound state goes actually further like this, so that's the positive side. So positive scattering length on this side, and that's the negative side. So it's repulsive here, attractive here. Yeah.
So let's thanks.